This is a graduation project for a bachelor's degree from the University of Tripoli, Faculty of Information Technology, Networks Department. Project title: Performance Evaluation of BFD over Rip, OSPF and EIGRP, a comparative analysis of routing protocols with and without bidirectional forwarding detection, BFD, by Enj Kenana Ali Alzara, Enj Heba Muhammad Al-Abbasi and Enj Wedad Hassan Al-Fala. SUPERVIED by Dr. Mahmoud Mansour. Table of content: 1 Project Goals, 2 Introduction, 3 Dynamic Routing Protocols, 4 BFD05, Network, Desgan, 6 Testing Methodology, 7 Results, 8 Conclusion. Goals of project: study the concept of network availability, install and configure a network simulation environment, e.g., NIELAB or GNS3, understand how RIP, EIGRP, and OSPF operate. Implement routing protocols, RIP, EIGRP, OSPF, without BFD, research the working principles and benefits of BFD, implement routing protocols with BFD enabled. Introduction. 1. Network availability is crucial for keeping services accessible with minimal downtime, as interruptions can cause financial loss and poor user experience. 2. Dynamic routing protocols, RIP, OSPF, EIGRP, ensure connectivity but have limitations in fault detection and convergence. 3. Bidirectional forwarding detection, BFD, enables sub-second failure detection, reducing downtime and improving reliability. Make decisions, learn routes, and share info. They use metrics to find the best path between networks. What is BFD? Bidirectional forwarding detection, BFD, is a protocol designed for rapid detection of link or neighbor failures, often within sub-second intervals. Its primary purpose is to accelerate failure detection compared to standard timers used by dynamic routing protocols. BFD mechanisms. BFD establishes a virtual session between two neighbors and exchanges small control packets at high frequency. Failure is declared if packets are not received within the configured interval. BFD can operate independently of routing protocols and can be integrated with RIP, OSPF, and EIGRP. Integration with routing protocols. BFD over RIP. Traditional RIP timers, update, invalid, hold down, flush, are long, leading to slow failure detection. BFD significantly reduces convergence time. BFD over OSPF. OSPF has faster convergence by default, but BFD allows near instantaneous neighbor failure detection, enhancing network responsiveness. BFD over EIGRP. EIGRP benefits from dual and backup paths. BFD ensures immediate activation of alternate paths upon link failure. Network DESGIN. Network components. Routers, 9 routers, R1R9, forming the core topology for routing protocol testing. LAN segments. Each main router connects to a LAN representing an internal network segment. Links. High-speed gigabit Ethernet links interconnect routers, with some used for failure simulation. End devices. PCs, hosts on each LAN used for generating and receiving test traffic. Protocols, RIP, OSPF, and EIGRP configured separately for performance comparison, both with and without BFD. Why this topology was selected. Balanced complexity. Enough routers, links to test RIP, OSPF, EIGRP without overcomplication. Scalability. Easily add, remove nodes or links. BFD integration. Supports testing BFD on critical links. Multiple test scenarios. Realistic traffic. Simulates enterprise traffic patterns. Simulation environment. Platform. NIELAB. Reason for selection. Flexible and supports industry-standard router images. Can emulate complex topologies accurately. Protocols used. RIP, OSPF, EIGRP, with and without BFD. Testing conditions. Same environment for all experiments. Testing methodology. A series of test scenarios were conducted on a controlled network topology. Each routing protocol was configured and evaluated under 2 modes, with BFD enabled and without BFD. Key performance metrics. Packet loss. Assesses the reliability of data delivery during link failures. CPU utilization measures the processing overhead introduced by each routing protocol and by the activation of BFD. Bandwidth consumption analyzes the additional network load generated by routing updates and BFD control messages. Results: packet loss. Packet loss, number of ICMP packet, RIP, without BFD, 115. RIP, with BFD, 40. OSPF, without BFD, 21. OSPF, with BFD, 3. EIGRP, without BFD, 8. EIGRP, with BFD, 0. Results: CPU utilization comparison. RIP, without BFD, 7%. RIP, with BFD, 15%. OSPF, without BFD, 9%. OSPF, with BFD, 23%. EIGRP, without BFD, 7%. EIGRP, with BFD, 26%. Results: percentage of bandwidth consumption comparison. RIP, without BFD, 0.06%. RIP, with BFD, 31.22%. OSPF, without BFD, 0.26%. OSPF, with BFD, 0.64%. EIGRP, without BFD, 0.45%. EIGRP, with BFD, 0.76%. Conclusion: this project evaluated the impact of bidirectional forwarding detection, BFD, on the performance of RIP, OSPF, and EIGRP. Each protocol was tested with and without BFD. Results showed that BFD significantly reduced failure detection and reconvergence times, especially in OSPF and EIGRP, while RIP saw modest improvements. Overall, the study confirmed that BFD effectively improves routing performance and fault tolerance, though careful parameter tuning is essential to balance efficiency and resource usage.